This video acts as a report that serves to analyze flow characteristics around a cylinder. Tests were done at varying Reynolds numbers for the purpose of comparing the resultant flow regimes that are produced. Additional tests were done with trip strips placed on the cylinder in order to trip the boundary layer at the desired location, allowing for the analysis of an induced turbulent boundary layer. Vortex shedding is also of interest. Video of flow behind the cylinder was taken and analyzed in order to find the vortex shedding frequency. It was found that as the Reynolds number increased, the coefficient of drag decreased. The boundary layer trip strip only caused a significant change in the highest Reynolds number tested, but it was not definitive that the boundary layer entered the turbulent regime.
Cylindrical shapes are very common and can be seen in the design of buildings and various other structures, such as airplanes and rocket bodies. When a fluid flows around a body, vortices are shed at a certain frequency depending on the Reynolds number. According to Gio-san, if the vortex shedding frequency matches that of the natural frequency of the structure, steady oscillations can occur, which can pose complications to the integrity of the structure. It is important to study and understand the dynamics of the flow around cylinders so that structural failure can be avoided. It is often beneficial to force transition of the boundary layer to turbulent in order to delay the separation point on the cylinder. Doing this reduces drag by minimizing or eliminating recirculation zones on the body that increase drag. This method is often used in golf balls, sailplanes, and speed skaters. Commonly used methods to induce a turbulent boundary layer during experiments are zigzag strips, sandpaper, and circular wires. The hypothesis that was proposed for this lab was that inducing a turbulent boundary layer would delay the separation point of the flow over the cylinder. This separation can be seen visually, as well as through the pressure data acquired during the experiment. Comparing the tripped and untripped flow around the cylinder with the tripped flow should have a higher average pressure reading towards the back of the body.
Listed here is the nomenclature and equations used throughout the experiment. The first equation is the Reynolds number equation. The second equation is the equation to find the coefficient of pressure. The third equation we used to find the velocity, derived from Bernoulli's equation. The fourth equation was used to find the coefficient of drag from the coefficient of pressure. The cylinder lab was conducted in Cal Poly's low-speed wind tunnel, which has a top speed of 58 meters per second and a fan with a max RPM of 1200, controlled by the variable frequency drive. Data was collected while the wind tunnel was running using LabVIEW 2015 and scanning valve ERAD 4000. The experiment occurred on February 23, 2017 from 1:40 p.m. to 3 p.m. The temperature ranged from 17.8 degrees Celsius to 17.2 degrees Celsius and the pressure stayed constant at 1012.8 hectopascals. The cylinder used for the experiment had a diameter of 12.65 centimeters and a length of 0.889 meters, with 24 static pressure points evenly spaced around the circumference of the cylinder. For our mechanism to trip the boundary layer, 80 grit grip tape was chosen, traditionally used for anti-slip surfaces. It allowed for a sandpaper surface with an adhesive backing that allowed for easy and secure application. The consequence of using the grip tape was the highest roughness of the sandpaper available was 80 grit, and according to AERO, rougher sandpaper leads to a higher chance of full separation of the boundary layer. According to Slagen, zigzag strips are much more effective in tripping the boundary layer than sandpaper due to the fact that sandpaper requires a thicker strip and tends to create a more randomly turbulent flow. This experiment combined the two methods into one zigzag sandpaper strip in order to more effectively trip the boundary layer. A straight sandpaper strip was used to trip the boundary layer on the lower half of the cylinder to potentially examine the differences in the two tripping methods.
The cylinder was visually inspected for any anomalies at the start of the experiment, and all 24 pressure ports were smoothed to the surface of the cylinder. A smoke machine was placed at the inlet of the wind tunnel to allow for visualization of the flow, and bright floodlights were positioned on top of the wind tunnel in order to make smoke more visible. Then the wind tunnel was turned on to an RPM of 100 and a settling time of 30 to 45 seconds was allowed before collecting data. While data was collected, video and photos of the flow around the cylinder was taken using a Canon DSLR camera and slow motion video was taken using an iPhone camera. This was then repeated at RPMs of 200 and 300. Repeat readings and videos were taken as the wind tunnel was stepped back down. Once the wind tunnel was completely shut down, the doors of the test section were open and trip strips were placed on the cylinder. One trip strip, approximately 1 centimeter thick, cut in a zigzag pattern, was placed approximately 45 degrees above the horizontal on the front face of the cylinder. The other trip strip, approximately 1 centimeter thick and straight, was placed 45 degrees below the horizontal on the front face of the cylinder. The trip strips were cut from 80 grit grip tape, and the placement of the strips was visually estimated. Once the grip tape was placed, the test section doors were closed and the wind tunnel was started up again. Readings and videos were taken at 100, 200, and 300 RPM. Then, while the wind tunnel was at 300 RPM, the green laser sheet was positioned on top of the test section in order to better illuminate the smoke. Video and recordings were then taken as the wind tunnel was stepped back down.
Shown here is a comparison of the cylinder pressures at Reynolds number 2.6 times 10 to the fourth. Due to the fact the test was operating at a low RPM, the pressure differentials on the cylinder were relatively low. This leads to a relatively similar graph for both the rough and clean runs. The graph shows a higher pressure where the flow is hitting the cylinder and a relatively lower pressure at the back end of the cylinder. In the coefficient pressure graphs, again, they are very similar due to the fact that the tunnel was running at a very low RPM. This graph gives a non-dimensionalized view of where the high and low pressure points are on the cylinder. As we progress through the video, notice how all of the clean coefficient and pressure graphs are essentially identical. The same relationship is shown graphically here to reinforce that the smooth and rough cylinders have very similar results. It also shows the data that was found compared to the ideal laminar flow approximation, giving confidence in the data collected. The expected flow visualization is shown here in the diagram. All of the Reynolds numbers used fell into this range, so the same flow visualization was expected throughout the experiment, but the degrees of turbulence will increase with the rising Reynolds number. By analyzing the slow motion footage, it was found that the vortex shedding frequency is 6.4 Hz.
These are the graphs for the cylinder pressures at Reynolds number 6.25 times 10 to the fourth for both the clean and rough cylinders. Again, these graphs look very similar, but if analyzed closely enough, it can be seen that there is a slightly lower pressure on the back end of the cylinder. However, due to the very close resemblance, at this Reynolds number, it cannot be said for certain that the turbulent boundary layer was tripped. Next are the graphs for the cylinder coefficient of pressure. Again, due to the lack of difference between the two graphs, we are unsure if the boundary layer was tripped. This plot of the CP graph again shows the similarity of rough and clean runs. Vortex shedding frequency for this Reynolds number is 16 Hz. It is important to note that the frequency increased from the previous run. This is because the vortex shedding frequency is directly related to the value of the free stream velocity.
Here are the graphs for a Reynolds number of 1 times 10 to the fifth. Although difficult to see at first, the low pressure zone at the rear of the cylinder is larger for the clean run as opposed to the rough run. Unlike the previous graphs, these graphs are different enough to say that there is a change in the boundary layer. Because of the slightly later separation point and the smaller low pressure zone, it can be assumed that the change in boundary layer was towards the turbulent regime. However, it cannot be confidently said that it was fully tripped. Here you can see the coefficient of pressure graphs. Again, these graphs show a significant enough difference to determine that there is a slight change in the boundary layer between the clean and rough runs. Graphically, you can see this difference represented here. The frequency of the shedding at this value is 24 Hz. Again, it has increased because the Reynolds number increased.
Comparing all of the clean cylinder pressure graphs to each other, it can be seen that all portrayed similar pressure characteristics, with a high pressure at the leading face and a lower pressure at the trailing face. However, it can be seen that as the Reynolds number increases, this difference becomes larger and more prominent.
Some error is present in the data due to the creation and placement of the trip strip. The angle and size of the zigzag pattern was not calculated nor measured, so the angle of the zigzags were not constant through the entirety of the strip. Furthermore, the placement of both strips was estimated from a lab member outside of the test section. The angle of the placement was at a 45-degree angle, but since this was not measured, there is no way of knowing if the strips were placed accurately. Also, the trip strips were very long, so it was difficult to keep them straight as they were stuck down to the surface of the cylinder, resulting in a slightly skewed placement, circled in the red in the photo of the trip strips here. All of these factors of error potentially contributed to error in tripping the boundary layer. The aim was to induce a turbulent boundary layer, but it did not seem to transition to a fully turbulent.
According to the University of Illinois, the coefficient of drag of a cylinder can be calculated by taking the integral of the coefficient of pressure multiplied by the cosine of the angle from 0 to pi, where the 0 angle is the front of the cylinder facing the wind flow. The coefficient of pressure was calculated at each pressure port along the cylinder, and then Simpson's method was used to calculate the integral for the coefficient of drag. The resulting coefficients of drag were then plotted against Reynolds number. The coefficient of drag for a rough cylinder is lower than that of a smooth cylinder, showing that tripping the boundary layer causes the drag forces to decrease. The coefficient of drag ranges from a maximum of 1.5 at 100 RPM to a minimum of 1 at 300 RPM. Compared to the values taken from Miami University for an ideal smooth cylinder, our calculations are well within the norm for cylinders. In the coefficient of drag plot made from the lab data, it can be seen that the coefficient of drag does not vary too much between clean and rough runs until the higher Reynolds number at 300 RPM. At this Reynolds number, there is a distinct difference between the coefficients of drag. The coefficient of drag for the clean run is approximately 1.2, while the coefficient for the rough run is approximately 1.05. It should also be noticed that in the 100 RPM runs for a clean cylinder, one of the calculated coefficients was much higher than the other two. This can be due to a possible error. It suggests that something changed between the runs, such as the outside door opening while we were recording data. Also, due to the low RPM of the fan, the amount of pressure felt by the cylinder is so low that the data collection is difficult.
This lab analyzed the flow around a cylinder at multiple Reynolds numbers, with both a clean surface and a surface with a boundary layer trip. Results found from the clean surface reflected results theoretically expected. Results from the trip surface were inconclusive because they did not show the magnitude of difference expected. Therefore, it was assumed that the trip did not cause the full transition into a turbulent boundary layer on the surface of the cylinder. Future experiments should investigate different methods of tripping the boundary layer in order to better achieve turbulent flow around the cylinder and better analyze the effects of delaying the separation point. It would also be beneficial to extend the experiment to higher Reynolds numbers in order to further observe the effects of the flow around the cylinder.